Thanks, Bill. I probably should have chosen a shorter title, I think. Okay, so my name's Scott Donnelly. I work for a company called Balyasny Asset Management. Balyasny is a global investment firm with over $24 billion of assets under management and 2,000 employees globally. We're active across a variety of investment strategies. And before I start, I should emphasize that any views and opinions I express today are mine and not necessarily those of my employer. At Balyasny, I work as a lead engineer on the macro data platform, and I'm also one of the 7 new Apache committees that Ryan mentioned this morning in the keynote, with most of my contributions, well, all of them being on Iceberg-Rust. So I'm here to talk today about a project I've been working on called Cheetah, as well as my experiences with Iceberg-Rust. Cheetah, so the requirements, we were looking for a query engine for our Iceberg tables. We only needed to handle simple queries with no aggregation really, but we had quite tight latency requirements. So the faster the better really. My users start to get unhappy when queries take longer than a couple of seconds. And initially we took an interim approach of embedding PyIceberg within our existing Python API service. But as a Rust developer, I wanted to see if there was a Rust equivalent of PyIceberg that I could use to potentially build something with Rust instead. Turns out back in February 2024, the answer to that was no. Iceberg-Rust was still in very early days. It wasn't even really possible yet on the main branch to retrieve any rows. But it seemed like a really exciting project with a lot of scope to get involved with and to make an impact. So I started to help out in my spare time. My first contribution I mentioned there was a refactor of an existing PR that made it possible for a table scan to actually return some rows, as long as what you was after was the entire table and all the columns. But over the next 6 months, I worked on gradually extending the capabilities of Iceberg-Rust to the point where it had the kind of core set of features needed to be usable for real-world usage on the read side. And a big thanks to Renji and Xuanwo, who are the kind of leaders on the Iceberg-Rust project. They've been invaluable, and I kind of count those guys as friends now. So 6 months down the line, now that Iceberg-Rust was a bit more feature complete, it was feasible to use it as a query engine to ideally replace our Python-based service. So the prototype architecture looked something like this. So Iceberg-Rust would form the core, with Data Fusion's SQL parser library being used to parse SQL requests into an AST, which we'd then transform into an Iceberg-Rust filter predicate. And we used the Tonic library to expose the query engine as an Aeroflight gRPC service. Since the main use case, though, was for queries from Python services or Jupyter notebooks, I built a Rust client library that handled the quite fiddly mechanics of interacting with Aeroflight, and used Pyo3 to create a more user-friendly Python client library that just takes a string of SQL and returns a POL as data frame. So I mentioned Aeroflight. If you're not familiar with Aeroflight, it's a gRPC-based framework for implementing high-performance data services. And it splits the data retrieval into 2 phases, a plan phase and an execute phase. So the plan phase, get flight info, takes a query and returns 1 or more tickets back to the client. And then the execute phase dispatches those tickets to servers, which then execute the plan that's embedded within the request. And the data is then streamed back to the client as a stream of arrow record batches. So Iceberg-Rust also splits the scans into a plan phase and an execute phase. The plan phase returns a list of file scan tasks, which are analogous to Aeroflight's tickets, and the data from Iceberg-Rust scans are also returned as a stream of record batches. So Aeroflight and Iceberg-Rust are really a kind of great match for each other. And looking at this, you might ask why there are 2 phases here. Why not just combine these? Is this not just needless complexity? And for a single server solution like this, then yeah, you'd be right. That would be more straightforward to combine these. But where Aeroflight comes into its own is really when you have more than one server handling the execution. So what you can do is then split the execution phase into multiple tickets. And the tickets contain the host address of the server that will respond to them. And this allows you to parallelize the execution across multiple servers. And this was something that I was really keen on doing with Cheetah. So once we built an initial prototype, the initial test showed that the performance was quite some way from where we needed to be to meet the latency requirements that we set up front. So we were seeing kind of multi-second responses for even really small queries. So we broke out the profiler, ran the profiler across this, and this showed that, as you'd expect, really, the majority of the time was spent waiting for S3. I think Ryan alluded to this morning. You have those 3 serial requests that are effectively unavoidable. And also, the profiling indicated that parsing was also pretty time-consuming as well, parsing the manifest list, and so on. So a cache seemed to pretty much the obvious improvement to make, and also that it would be better to cache the parsed objects rather than the raw data themselves. So the result was the object cache, which was a feature that I worked on that was merged into Iceberg-Rust back in August. So parsed manifest lists and manifest objects cached in an LRU cache in memory. And this improved the performance of the query plan phase by about 100 times when the cache is warm compared to prior to the cache being present. So now we're able to serve up our query plans about 100 times faster once the manifests and the manifest lists are in the cache. And the performance by now is a lot better, especially for the small queries for which the plan represented quite a significant proportion of the total execution time, but still not as fast as I needed it to be. So this left a couple of avenues left to explore to improve the performance on the execute side. And so the first approach was reducing how much data that we retrieve from S3 in the first place. So you've probably seen the diagram on the left in the Iceberg spec already. So the Iceberg's manifest lists and manifests contain metadata that's used to prune down the list of data files so that only data files that contain that can contain rows matching a query's filter need to be actually scanned. But you can go further than this in trimming down how many rows you need to apply your filter to by making use of the metadata present within the Parquet files. So Parquet files, they're not just simply monolithic tables. They can contain 2 extra layers of metadata that can be used to filter down the number of rows that you need to actually scan. So within the Parquet file, the data is grouped. It's kind of chunked into row groups internally, and you can think of a row group as almost like a horizontal slice of a table. And often you'll find if you've been doing writes with Iceberg, then you generally would see that there's only a single row group for the entire Parquet file, so you might not even be aware that they exist. And you need to change the write properties within Iceberg in order to get row groups that are small enough so that you get multiple row groups within a single Parquet file. And we found best results when you've got 8 to 16 row groups per file. And then within each row group, the data for a given column is then further split down into smaller chunks called pages. So as well as the data section, we also have the footer in the Parquet file, and this is where we find those 2 extra levels of metadata that I was referring to. So you'll find a row group metadata, which unsurprisingly has metadata about each row group, and also optionally a section that's called the page index, and this contains page level statistics for each page with each column inside each row group. So the row group metadata in the Parquet footer contains statistics on each column for each row group, and so you can use you can apply the query filter predicate to the row group statistics in order to determine if any rows in that row group can possibly match the predicate. So in cases where the stats indicate that no possible rows could match, like in row group 1 and row group 3 here, you can skip those row groups entirely, and since you can do range queries on S3 and other object stores, you can skip directly to just the row groups that can possibly contain data, so avoiding those fetches entirely. And the Parquet footer, as I mentioned, also contains optionally the page index. I think by default you might see this present if you have your writes being done by something in Java, but if you're having your writes being done by Iceberg, you may not see the page index by default. And this page index contains the same statistics as the row group metadata, but at the level of individual pages within a column chunk. So this lets you skip even more. So you only need to scan the pages within a row group whose statistics show that they could contain data matching the filter predicate. So I added row group skipping to Iceberg-Rust back in August, and also page skipping back in September. And Iceberg-Rust became the first of the Iceberg libraries to implement support for page skipping. So this was quite exciting for us in Iceberg-Rust to be ahead of the other Iceberg libraries. So with those in place, I kind of excitedly set up some test queries to see quite how much of a difference this page skipping and row group skipping was going to make, and see if I was any closer to my performance requirements. And surprisingly, a lot of the queries actually got slower. And after breaking out my trusty profiler again, this kind of indicated that the time taken to parse the page index inside each Parquet file often takes longer than the time that it's saved from the scan, which was a little bit annoying. So I realized that now that we'd had a cache for the manifest lists and for the manifests, if we wanted to get any real world gains from the page index, we'd also need to cache the parsed Parquet metadata as well. So the second avenue that we explored to improve the performance on the execution phase was to take advantage of the parallel execution model that the Arrow Flight API that I mentioned enables. So the approach that we took is to group up all of the constituent data files into shards. And right now, this is done in a really simple way. We simply hash the file URL and take the hash value modulo the number of Cheetah instances in the cluster to get the shard ID for the given file. This is not ideal. If you change the number of nodes in the cluster, your shards go all over the place, so don't do that. But at least it was a start. And so each shard is now the responsibility of a different Cheetah instance within the cluster. And so an incoming query can hit any node, and so we want to cache the metadata on all the nodes, but the resulting file plans that come out of a query are grouped into tickets by shard. So files that are in shard 1 get added to a ticket that gets sent to, that gets addressed to node 1. Files that are in shard 2 get sent in a ticket to node 2, and so on. And so by doing this, it meant that it was feasible for us to start caching the data in some cases as well as the metadata, because each node's cache is now non-overlapping. So we can make much better use of the available memory. And also, it gives us the capability to horizontally scale out to as many nodes as we want to give us as much cache space as we want. So we don't need this for every table. That would be pretty crazy. But at least for some of our most heavily trafficked tables, this was able to give us a big performance improvement. Not only that as well, but sharding the tickets as well as being able to take advantage of the cache like this, we also get a speed up in parallel because of the parallelization of the execution. So the speed up is pretty much proportional to the number of nodes handling the query. So with this in place, we have our enhanced object cache that caches parsed manifest lists, parsed manifests, parsed Parquet metadata, and optionally the raw Parquet metadata. So with this in place, with a warm cache, queries can now be 100 times faster from the file plan perspective, and now also 100 times faster from the execution perspective. So with these in place, we were able to get queries in as little as 60 milliseconds, and that's including the gRPC round trip time to make the plan, get the plan back, and execute and come back. So pretty decent. We see throughput as high as around 17 million rows a second was the fastest that we've seen from an 8-member Cheetah cluster. So this was great for queries to a warm cache, but users were still complaining because our P90 latency was still just as bad as before when queries require data that's not in the cache. So we extended Cheetah with a cache warmer thread that runs in the background. And we have this kind of two-layer concept of warm and hot tables. So when we add a table to the warm list, we're effectively keeping the metadata warm for those tables. And we also have a shorter hot list as well, where we keep the data warm as well as the metadata. And so to warm the metadata cache for a table, all we need to do is perform a file plan with no filter predicate, because the object cache is a read-through cache. So this primes the cache with all of the current manifest list and all of the manifests. And then we take the result of that file list and query the object cache for every file's Parquet metadata in order to warm the warm table cache. And for tables in the hot list, we do all of that, but also query the object cache for the raw data for the file as well, which has the effect of priming the read-through cache for the data sections. So this was where we were when I submitted my abstract with the 60 millisecond figure that I mentioned in there. But since then, we've gone even further. So I broke out my trusty profiler again, and this showed that 40 milliseconds of the 60 milliseconds in these fast queries was actually spent waiting for the metadata JSON from the catalog. And we'd also at this point started seeing some slowdowns during periods of heavy load. And this was caused by slow responses coming from the catalog as well. So I decided to add one final cache to cache the results of the catalog's load table method. And we only cache it for 5 seconds, but I mean, in those 5 seconds, we could get dozens and dozens of queries. So it's actually pretty effective and only adds a small amount of staleness to queries to the table. So this let us hit our new fastest query time of 22.7 milliseconds end-to-end for a query on an Iceberg table, which, yeah, pretty happy with that. And also had the side benefit of now getting much less load on the catalog, so we don't see the same kind of issues that we had before where we were getting long delays. Yeah, I'm going to skip this because for time constraints, but we've got a few other items that we've managed to do in terms of enhancements that we'd like to contribute back to Iceberg-Rust that should be coming over the next few months as well. Yeah, so now with a combination of the cached parsed metadata, the extra levels of predicate pushdown, the sharded distributed cache, the short-lived table metadata cache, we're able to finally meet and exceed the performance targets that we had set out in the requirements. The cached parsed metadata lets us perform the smallest queries in as little as 23 milliseconds end-to-end. And the distributed execution model allows us to get really good parallelization for larger queries, like in this example where we have a 5 million row query returning in 0.6 of a second. Yeah, and as mentioned before, we've seen peaks of up to 17 million rows a second for heavily parallelized queries, and the bottleneck then actually becomes the network bandwidth of the client itself. We're seeing like 4 gigabits per second of traffic heading back to the client. So in terms of the future, so where we want to go from here, we're going to have a look at some other features that we've built that will hopefully come soon to Iceberg-Rust, as well as some of the things that we'd like to add to Cheetah as well. So the Iceberg-Rust developers have recently agreed on an approach for distributed tracing using the tracing crate from Tokyo. We've already been using this locally in our Iceberg-Rust fork, collecting the traces as open telemetry traces and exporting them via OTLP. And we're also able to propagate the trace context from the Python service in which we have the Python client over the kind of language layer into the Rust client, then across gRPC into the Cheetah server, and then into Iceberg-Rust itself. So we're able to get quite good insight on distributed traces across the full lifetime of the request. And this has given us quite a lot of insight into where the time has been spent on each query, which has proved really invaluable for both for getting further performance improvements for Cheetah, but also in how we optimize our tables. Iceberg-Rust has also recently settled on using the metrics crate so that we can start exporting metrics from Iceberg-Rust. We've already been doing this as well, using the metrics crate and using the Prometheus metrics exporter. So you can see here we've got exposed metrics on the object cache, so we can see statistics on cache hits and misses for each type of object that we have in the cache. So we can see, yeah, pretty good hit rate there. Iceberg Java also has scan reports, but we don't really have that yet in Iceberg-Rust. But what we have been able to do is add attributes to the traces that gives us similar kind of capabilities via the exported traces alone. So you can see here we're able to see the files that were hit for each query in the plan phase, and looking at the trace for the execution phase. We can see how many rows and row groups were filtered out as part of that execution step. So some of the things that we don't have yet. Iceberg-Rust doesn't yet have support for delete files on the read path, but this is really close to being completed. Something that I've been working on for a few months, and hopefully will land very soon. One other thing that we would really like to see, I think Ryan again hinted on this morning, is kind of more cache awareness. And what I'm referring to here with cache aware maintenance is really the kind of rewrite manifests and rewrite data files jobs. We think that if we could enhance those to become a bit more cache aware by kind of segregating manifests containing non-recent data from recent data, and similarly for the data files, so that let's say all the writes within a current day end up only touching the small subset of the data files and the manifests, and this allows the cache the remainder to stay cache resident for a lot longer time, because those don't get touched by the maintenance jobs on a kind of intraday basis. The next thing that we'd like to do, this is more of a Cheetah thing now than Iceberg-Rust, is this distributed shard balancing. So yeah, I mentioned that the scaling up and scaling down the number of nodes in a cluster effectively throws your cache all over the place, because we're using a hash and a modulo to determine which shard a file ends up on. So what we'd like to do would be to move to an approach where we have a fixed number of shards, maybe 100, 200 shards, and then we dynamically move those shards around between different nodes using some kind of a consensus-based approach. And what that would let us do is also improve the resilience of the service as well, because I guess if you think about it, if you're sharding but you don't have redundancy on any of your shards, then only a single part of your query has to fail for the entire query to fail, whereas we'd be able to dynamically allocate the same shard to multiple nodes, and that gives us a bit of extra redundancy. Another feature that we want to add is snapshot pre-warming. So this is where we'd like to stick with a already cached snapshot until the new current snapshot has been cached, and this would again help with our kind of P90 and P99 latency, really only at the expense of maybe just a few seconds of staleness. And also, one of the other remaining feature that we'd love to add is a kind of a work-based quota system. So the only one of the issues that we have at the moment is like kind of noisy neighbor effects, where if somebody decides to completely hammer the service, then we've got really no protection for other users against that. Yeah, so that's pretty much everything that I've got, and yeah, thanks for the opportunity to come here and make this talk, and yeah, I'd like to thank my employer as well for making it possible for me to come over here, and yeah, I'd like to turn it over for any questions if anybody's got any questions I'd like to ask. Thanks.
So is Cheetah available? Like, is it open source or is it proprietary?
No, it's not. It's not available open source. No.
Is there any plan to like merge these features into Iceberg-Rust or?
Quite a few of the features, yeah. Okay. So yeah, there's anything that I've mentioned on here that is not Cheetah specific and is something that would be usable within Iceberg-Rust. Yeah, we're looking to contribute that back.
Awesome. Yeah.
Zach.
How do you treat file size tuning versus like row group tuning and row group skipping? Because if you squint, you know, I think you could get, like, you could just say, oh, let's do like one row group per file, and then you can just shrink and enlarge the size of your files to get a lot of the same like granularity for skipping. Yeah, I was just curious how you grapple with that. Like, do you simultaneously tune file sizes and row group sizes to some degree?
So the approach we took was really just driven by experimentation, really. So we started off with the standard file size and the standard row group size. I think we settled on 128 meg file sizes and I think 32 meg row group sizes and around 20,000 entries per page. And really, I suppose it's more of a table by table basis. Really, we've just taken an approach to tuning them individually.
Well, first of all, a wonderful talk. We're working on the same sort of performance optimization for ClickHouse that you're doing here, so it was great to see the laundry list of their overlapping subsets, the optimizations we're doing and you've done. One thing I didn't see you discussing was external caching. So, for example, we've done experiments with, and some of our users have done the same using HTTP caches, which can have sort of miraculous effects because they will, take out, you can cache the effects of list objects and things like that, which are relatively expensive calls. And I just wonder if you have, I know that's a little bit outside of what you're doing, but have you experimented with that?
Well, I did kind of skip over it for time purposes, but the first attempt at the cache that we made, we use, so Iceberg-Rust uses, are you familiar with OpenDAL? It's a library that abstracts over different vendors' kind of object stores. And that has like a layered architecture, so you can almost build layers as plugins. And we first tried to just create a caching layer with an OpenDAL that effectively functions as an S3 cache.
Right.
And it works. It's quick to do and it works quite well, but you don't then get the benefits of caching the parsed objects. You then still have to parse it.
Right.
Yeah.
Which, so you because you want to keep that, like the parse JSON, you want to keep in memory as
exactly, yeah,
nice Rust or C++ structures.
And to give like some of the numbers, especially if the more columns that you have in your table, the longer it will take you to parse the Parquet metadata cache, because at the moment you can't tell Parquet to only store metadata for some of the columns, and you can see it as slow as like maybe 800 milliseconds for a single file.
Right.
So it can be pretty slow to do that. It effectively makes, unless you're caching the past Parquet metadata, then the page skipping is useless, effectively.
Right. And then a follow-on question, but in a slightly different area. So you've been talking about reads. The whole sort of notion of pre-flighting and then getting a series of tickets and then dispatching them to different hosts is a very powerful model. You're using it for reads. Do you have use cases where you need to do a similar thing for writes? And if so, what's your thinking about how to actually make that work on Iceberg?
No, so we don't, but I know that the Arrowflight protocol does include writes as part of the spec, but we've only really used it on the read side. So for us, whilst the read requirements are pretty tight latency requirements, on the write side, we've been able to find that we can meet our write latency requirements
using other mechanisms.
Yeah, using other mechanisms.
Okay,
yeah.
Thank you.
Thank you.
So I was wondering, about the Arrowflight piece. So the planning you said is you do the planning using the Arrowflight protocol?
Yeah, so the Arrowflight protocol has two phases,
right?
And it's very generic. So all the Arrowflight mandates is the shape of the kind of approximate shape of these tickets, and it specifies the internal as just bytes. So really, it's up to the application as to how it interprets that. So all we're doing is just storing the SQL string as the request payload. But it's more proscriptive about the tickets that come back. So generally, the ticket will contain one or more potential hosts that can fulfill that ticket, plus effectively some opaque data, which is where you encode the predicate and the table and so on. And
so I'm curious why you chose. is it for the whole gRPC mechanism that Aeroflight provides, so you're able to talk to the client, and is that why you chose Aeroflight versus building something of your own?
So it's a good match with Iceberg-Rust because they both both are returning the data as a stream of Arrow record batches. And Aeroflight already provide libraries that work out of the box with Tonic, the gRPC framework that we were using. So it meant that a lot of those pieces were already in place. And also it means, because Aeroflight is intended as a more general API paradigm, and it also provides, we're not using them, but it provides mechanisms for like data set discovery and so on. It also meant that if in future that Aeroflight becomes kind of more popularized, that maybe some clients may use the Aeroflight API directly rather than using our client wrapper.
Yeah. So I was wondering, because just one last question. Query planning or scan planning would be improved, let's say, on the Java world. Now you have this custom implementation running, then how will you get benefits out of that if you do this through the Aeroflight format?
Sorry, say that again?
So let's say, scan planning is probably going through massive performance movements for the Iceberg Java world. You would have, if you have to incorporate those benefits, you have to mimic that similar thing within your Aeroflight setup, right?
Not necessarily, and also the gains from Aeroflight are also on the parallelization of the execution side as well. Being able to stream back the data from the multiple executor nodes all at the same time and stitch it together back on the client side also gives a lot of advantages.
I just had a quick question on Cheetah, and does it include, within that system, you have to have somebody to handle like predicate evaluation and sort of like these query engine level, like CPU bound-ish tasks.
Yeah.
Is Cheetah, I'm curious, like what components of a query engine are included in Cheetah? So for example, who handles your expression evaluation? Are you like just using Arrow Compute or? Yeah.
So we use there's a data fusion Rust crate called SQL Parser. That translates a string of SQL into an AST, and because we explicitly have no requirements for aggregation. The kind of query engine that we require it's really the SQL part of it is really just a convenience over being able to specify which table you want to query, which columns that you want to project, and what your filter predicate is. And in fact, the reason why we went with using the SQL parser library was because we wanted to present this as a Python library wrapped in using Py03. It's way easier to just pass a string from Python into Rust than it is for us to like model the filter predicate in classes and do it that way. So It was kind of a side benefit actually, but it's made it a lot more usable because everybody knows SQL.
Yeah. What about, like, you still have to evaluate expressions, right? Like if you have min-max statistics,
Yeah.
then you have ultimately some,
metadata. That's all within the Iceberg-Rust library.
Okay.
Yeah,
okay.
Yeah, Iceberg-Rust handles all of the evaluation, like against the manifest and the manifest lists, and also Iceberg-Rust hands off to Arrow and the Parquet library for when it comes to the row level filter predicate application. So, yeah, we internally transform the Iceberg predicate into an Arrow predicate.
Got it. Okay, so you take no opinion on like an expression framework of your own, like an expression language of your own, nor like how to evaluate predicates really. You're kind of like pushing that down to Iceberg-Rust and
yeah, exactly. Yeah.
Okay, cool. Thank you.
Thanks. Thanks, everybody.